My name is Velilla, and I'm the presenting author of this poster, which is a collaboration between several teams, several research teams. In principle, the Institute of Science of Materials in Madrid, also the Institute of Millimetric Radioastronomy, and the Harvard-Smithsonian Center for Astrophysics, and also the Center for Astrobiology in Madrid, and the University of Toulouse, where we present the circumstellar chemistry, our results of circumstellar chemistry toward the evolved star IRC 10-16. In particular, the emission of silicon-carbon bond-bearing molecules. So, IRC 10-16 is an evolved star, which is a star like our Sun, but about 5 billion years older than our Sun. And in these states of stellar evolution, these stars lose a lot of mass, a huge amount of mass in form of gas, molecular gas and dust particles. And these objects are the main contributors to interstellar enrichment, and their study is important to understand the chemical complexity of the universe. So we studied with three of the most powerful instruments in the world, in particular three array of antennas, which are ALMA, NOEMA, and ESMA instruments. The emission of silicon carbide, silicon dicarbide, and disilicon carbide molecules. So what we are seeing here is the emission of observed with ALMA of silicon dicarbide. What we are seeing here is like a vertical cut of the circumstellar envelope, which is a spherical dust and gas envelope surrounding the star. The star is not seen. We are seeing only the spherical envelope, and silicon dicarbide is distributed like a circumstellar spherical cell. And also we have emission arising from the central part of the inner parts of the envelope. Here we see in more detail the observation with NOEMA, also corresponding to silicon dicarbide. And in the lower panel, we have the emission from silicon carbide. What we can extract from these observations is that silicon carbide is present in the innermost part of the silicon dicarbide is present in the innermost part of the envelope, but silicon carbide is not. This means that it's related to dust formation, since dust grains are formed in this part of the are formed in the atmospheres of the star. So they are participating in the formation of dust grains. And in this map here, we can see the SMA brightness seen with the SMA, the brightness distribution of disilicon carbide, which is giving us the information of its distribution. It's quite concentrated in the inner parts of the envelope. It's not a very compact distribution, but it's distributed in this region. And this work represents a multidisciplinary approach to understand the formation of the circumstellar chemistry of these molecules. This has served as a collaboration, and we found, thanks to the laboratory work done in Harvard, the 112 lines of the silicon carbide. So it's important to have synergy between observational and laboratory works in order to characterize this type of chemistry of silicon carbon bond-bearing molecules, which are closely related to dust formation in evolved stars. And as I said before, this is important because of the relation of these molecules and the evolution of the universe in terms of chemical complexity, and how this and the important role that these objects have in this context.